Hi, I'm Dongyoung Choi from KAIST Korea. This is a collaborative work with Hyeonjoong Jang and Min-H Kim. In this video, we will present an omnidirectional local radiance fields method from dynamic videos. It's called OmniLocalRF. An omnidirectional camera can capture scenes in 360 degrees. The captured image can be mapped in the spherical coordinates. Also, it can be represented as an equirectangular image, of which the axis denotes azimuth and zenith angle respectively. If we have multi-view equirectangular images with their camera poses, we can synthesize the novel views from a virtual camera. Now, we call it as omnidirectional view synthesis. However, there are two main challenges to synthesizing omnidirectional views from casually taken 360 videos. Firstly, the previous works mainly use images for training whose camera trajectories are narrow and limited. For example, if we use training data captured by swinging the camera over the head, we can only reconstruct the limited range scenery. Second, unless we use specific hardware such as a drone or remote controller, the photographer should be captured in the image dataset due to the nature of the omnidirectional camera geometry, and it causes severe artifacts during view synthesis as a dynamic object. We present OmniLocalRF, which can synthesize novel views of static scenes only from 360-degree videos by automatically removing dynamic objects even without camera priors. TensorF decomposes spatially embedded neural features into the line vectors and planes. For color estimation, the method concatenates the extracted features and feeds them to the shallow MLP. TensorF leverages all the features to estimate the density and trains the model by photometric loss between the rendered images and ground truth images. For view synthesis from long videos, the local radiance fields method was proposed. It progressively optimized multiple TensorF with the camera poses of input frames. The method inserts the input frames into the TensorF block and jointly optimizes the poses with the TensorF. When a new frame located quite far from the current TensorF block is added, then the method adds a new block. This optimization process continues until the end of the video. But using local radiance fields directly for 360-degree videos is susceptible to artifacts caused by dynamic objects in the scene, because each tensor block only considers the locally adjacent frames. There is a difference between the conventional perspective camera and the omnidirectional camera with respect to the field of view. In a perspective camera, 3D points captured by previous frames often cannot be observed in the posterior frame due to the limited field of view. However, the omnidirectional camera can observe most of the scenes captured by previous frames unless it is occluded by objects within the scene. In our work, as the camera trajectory goes from left to right, TensorF blocks and adjacent frames are jointly optimized progressively. Here, the red TensorF block presents the currently optimized block and frames. We can bidirectionally optimize the current and previous radiance fields using distant frames. By employing the frames used for training the previous TensorF block, we can refine the current TensorF. Now let's call it a 4-step. We additionally update the previously converged blocks by the frames for training the current TensorF and call it a backward step. In the 4th step, we refine the current TensorF using the previous frames. We render the points from the current frame through the current TensorF and project them to the previous frames. Here, we get the color at the projected point by bilinear interpolation. From the projected pixel location, we render the depth and color using the previous frame and current TensorF simultaneously. If the rendered distance difference between two TensorF is lower than the threshold, we treat that the rendered 3D point is mutually visible by both frames and leverage the photometric adder to refine the current radiance fields. In the backward step on the other way, we update the previous tensor using the current frames. We inverse the source and destination in the fourth step and update the previous tensor using the photometric adders. We also propose a motion mask module to mask out the dynamic objects automatically during training radiance fields. First, we create a multi-resolution feature grid for every frame. When we render the color of the pixel UV at the kth frame, we extract the corresponding multi-resolution features from the kth feature grid and generate feature code Z by concatenating them together. We feed these codes to shallow MLP and estimate the colors of dynamic objects and motion masks. Then, we render a static scene by volume rendering and render a final output frame by compositing the dynamic object static scenery. We supervise dynamic colors and final output using the ground truth images and regularize the mask outputs. These are the motion mask estimation results by our method while training radiance fields. Our method can successfully mask out the dynamic objects, even shadows, which are hard to segment by pre-trained models. The final colors of the dynamic objects are multiplication with the mask values and the dynamic colors. We can resolve the factorization ambiguity issue by supervising dynamic colors using ground truth. It enforces the mask values close to binary values and helps the model obtain a clear motion mask. For fair comparison, we exclude the dynamic objects of all the test scenes manually when computing the metrics. While our method can remove the dynamic regions well, other works still suffer from after-image-like artifacts that deteriorate the image quality. These are result videos of our method compared with existing methods. Our method can remove the dynamic objects clearly while maintaining their details in unpainted regions. In order to evaluate the camera pose estimation accuracy, we create 3 synthetic videos that including dynamic objects, and then estimate the camera trajectory while training view synthesis. While trained by videos including dynamic objects, our method can achieve higher quality than other existing methods trained with static-only images. We also evaluated how robustly 3 different methods can estimate the camera trajectory from dynamic 360-degree videos. Ours shows most accurate results thanks to our bidirectional optimization scheme. This is an ablation study of our method when bidirectional optimization is not performed. Our model overfits to the adjacent frames, slightly degrading the quality. Also, not using a motion mask severely affects the rendering quality due to the absence of handling dynamic objects. We have presented a novel method, so-called OmniLocalRF, for omnidirectional view synthesis from dynamic 360-degree videos without requiring camera priors and motion mask. Our approach integrates local radiance fields with a novel mask module and bidirectionally refines distant radiance fields block to remove dynamic artifacts and fill in occluded regions with details. Our method also can estimate a camera trajectory robustly from 360-degree videos even with dynamic objects. Thank you for listening. If you want to know more about this, please visit our project website.